Before we start on the main topic for today, I just want to mention a couple of terms that I want to make sure that you guys know about trig functions and the way that they behave. So the first thing, which I'm not sure if I ever stated this as a definition specifically, is the idea of a reference angle. So a reference angle, this is simply given an angle, this is the smallest angle to the x-axis. So you remember when we were talking about computing different trig functions, we would look at the unit circle because, of course, the trig functions come from thinking about the terminal points on a unit circle. And there's an example of a unit circle, sort of. And so what we would say is, like, let's say that I'm working with this angle over here, and this is an angle of 5 pi over 6. Well, the reference angle would be this angle that I'm marking with the double arc symbol here. That this angle makes with the x-axis, okay? And that is, of course, going to be an angle that has a size of pi over 6 in radians. So the reference angle is just another way of talking about that smallest possible angle that you can make with the x-axis. If I were to talk about, let's say, this angle down here, this would, strictly speaking, if we just want to talk about what is this angle here, well, this is going to be an angle of 5 pi over 4. Sorry, hopefully that's sort of readable here. But the reference angle here would be pi over 4, because the smallest angle between this radius, this radial line, and the x-axis is pi over 4. So the reference angle is just the angle that you use here. Now, why do we call it a reference angle? Well, the reason is because if theta sub r is a reference angle for theta, then the sine of theta is equal to plus or minus the sine of theta r, and the cosine of theta is equal to plus or minus the cosine of theta r. In other words, you can find these by using the reference angles, and then to figure out is it positive or negative, you just ask yourself, is sine or cosine positive or negative in this quadrant? So in quadrant 2, for example, we know that sine is positive and cosine is negative. And remember, you don't have to just memorize which quadrants is sine positive, which quadrant is sine negative, and similarly for cosine. You don't have to memorize that really, because if you remember your unit circle definition, if you remember that the sine is the y-coordinate and the cosine is the x-coordinate of the terminal point, then you're really just asking, in this quadrant, is my y-coordinate positive or is it negative? Well, over here in quadrant 2, it would be positive. So that means sine is positive. The x-coordinate in quadrant 2 is negative. So that means the cosine is negative. So using the reference angles, the reason that this is so nice is because it means you only really have to memorize what happens in this first quadrant in terms of sine and cosine. The other terminology that I did not explicitly mention, I don't think, maybe I did, and I just don't remember this, is whenever we are dealing with a periodic function, another thing that we can think of with periodic functions is something which is called the frequency. And the frequency is simply the reciprocal of the period. So if we write F for the frequency and capital T for the period, for various historical reasons, capital T is often used to represent the period. then what we can say is that the frequency is 1 over the period, and the period is 1 over the frequency. Now, this isn't something that we need to worry about too terribly much here, but it turns out that there are a lot of applications where you have periodic functions where it's sometimes more convenient to think about the frequency than the period. And what is the frequency really measuring? Well, the frequency is really measuring how many cycles do you get over a given interval. So, for example, if the period is, let's say, 2 over 5, the frequency is 5 over 2. And what that means is that in an interval of length 1, you will get 5/2 cycles. Or in other words, over an interval of length 1, your function will complete 2.5 cycles. If you're given the frequency, then you can figure out the period by just taking the reciprocal. So for example, if the frequency is 60 cycles per second, then the period is 1 over 60, and that'll be in seconds per cycle. What this means is you're going to get 60 cycles every second. Now, I chose that number because that's actually the frequency at which our alternating current in our houses is running. At least I think it's 60. Maybe it's 120. I know it's 120 volts, but this is something different. Anyway, the point is that this is a rather common thing to see. The 60 cycles per second is a fairly frequent thing that you will see. And by the way, cycles per second, if you go into physics, you'll know that these are called hertz, symbolized by Hz. It just means cycles per second. So, analyzing this stuff mathematically, usually we really are interested in what is the period. But sometimes for different applications, instead of talking about the period directly, people will prefer to talk about the frequency. And so you should understand how to deal with that. All right. I want to recommend also that you guys make sure that you watch the videos for all of the things in Chapter 7 that they have on My Math Lab. I'm assuming here when I make these videos that you guys are also watching those to help you to make sure that you understand how to do the homework and to do the tests and all that kind of thing. So do make sure that you watch their videos too. Like I've said before, having different people explain the same thing to you is really a very good thing when you're learning, because sometimes you might understand their explanation better than you understand my explanation. Or maybe sometimes what they say is very confusing, but what I say makes sense to you and then you understand it. So hearing from different people, hearing kind of these different perspectives is really important when you're learning. Okay, so here's what I want to introduce today as our topic. This is the topic of inverse trig functions. Now, right off the bat, there is something that you should notice and that you should object to. The problem is this. Sine and cosine, and actually all of the trig functions, are not one-to-one. In fact, they are periodic, so they cannot be one-to-one. They keep on repeating themselves. They're not just not one-to-one. They're like super badly not one-to-one. They keep repeating themselves infinitely as we go off in either direction. On a graph, you would just see the same thing repeating itself forever. So very badly not one-to-one. Well, there is kind of a standard solution to this problem that we mentioned before when we talked about one-to-one functions. And the standard solution to this problem is we can restrict the domain. If I restrict the domain, if I pick it correctly, then I will get a one-to-one function on this restricted domain, and on that domain, I can define an inverse. Because once I have a one-to-one function, I can always define the inverse. That's no problem. The only issue is that I may need to restrict the domain first. All right, so let's take a look at how we can do that for sine and cosine. Now, I'd like to start with the sine function. The thing I want to say here is that when you start doing this, there are choices involved that you can make. There's lots of different ways that I could restrict the domain and make this function one-to-one. So we need to pick one of those. And the thing is that there is a convention for which one we pick. We could have made other choices if we wanted to, but this is the conventional one that we're going to use. So, the inverse sine function, which is sometimes called the arc sine, is constructed in the following way. Now, I want to sketch for you really quickly a graph of y equals sine x. This is not actually really quickly, I guess, because it's taking me a minute to do this, but okay, we know that what sine x looks like will be something like this. Now, what I would like to do is I'd like to pick my domain to be as large as it can be and also to cover all of the possible values in the range of the sine function. Now, remember, the range of the sine function is going to be from -1 to 1. And I want to make sure that I pick a domain that hits that entire range. But I also want to make sure that on that domain, it never repeats its values. And one way of doing that, and the way that we end up taking as our convention, is let's restrict the domain to the interval -π/2, +π/2. In other words, I'm restricting to this interval here. Now, why would I do this? Well, the reason, like I've said, is because I want to make sure I hit the entire range. And on this interval, I start out at -1 and I go all the way up to +1. So I do hit the whole range. Let's write that down, because that's an important thing that we want to have. So we hit the whole range, that's good. The other thing is we want to make sure that we never hit the same value twice. Well, we don't, because on this entire interval, the sine function is constantly increasing. It always, well, it's not increasing at a constant rate, but it's always increasing. Now, if you think about it, if I'm always increasing, I can never repeat the same value because I just keep on going up and up and up and up and up. Another way of thinking about this, if I start doing horizontal line tests here, obviously the horizontal line test fails on the entire sine function. Every one of these lines is going to cross the sine function many, many times as I keep on going here, right? But if I restrict myself to just this interval, then the horizontal line function is going to, horizontal line test, what am I saying? Horizontal line test is going to work. So because this function is always increasing on this interval, it is 1-to-1 if I restrict it to this interval. Now there's other intervals I could have picked, and they would have worked as well. For example, I could have picked maybe π/2 to 3π/2. From π/2 to 3π/2, this is also 1-to-1 because it's always decreasing, and we do in fact hit the entire range. So yeah, we could do it that way. But here's the thing. This is just the one that we've picked. You know, historically, this is what people use. So we followed that convention. So this gives us the definition of the inverse sine or arc sine. Sorry, I don't know why I didn't put the E on there. So, we define arc sine, which is usually just written as arc sin of x, which is also sometimes written as a sin of x, and a little bit confusingly, although I kind of like this notation honestly because it's very compact, it is sometimes written as sine inverse of x. The reason I say this is confusing is because this makes it look like it's an inverse function for the sine function, and there is no such thing because sine is not one-to-one. So you have to remember that this really is going to refer to a kind of a special definition that we're about to give here. So we define this in the following way. We want it to be the inverse of sine x on the interval from minus pi over 2 to positive pi over 2. So this means that y equals sine inverse of x. This is defined to mean the following two things are true. First of all, actually instead of y, let's use theta. So theta equals sine inverse of x means that the sine of theta needs to equal x, and the other thing is that theta needs to be in the interval from minus pi over 2 to positive pi over 2. So those are the two restrictions that we have, or the two parts of the definition that we have for the inverse sine function. Let me leave up that definition for a moment, and we will look at a couple of examples of using that definition. So let's start out by saying, let's suppose that I want to calculate what is sine inverse of, let's say, square root 2 divided by 2. Well, what I'm looking for here is I'm going to be looking for an angle theta with sine of theta being equal to square root of 2 over 2, but I also need theta in the interval from minus pi over 2 to positive pi over 2. That's also going to put this angle in quadrant 4 or quadrant 1. And we know that in order to get a positive value for sine, we need to be in quadrant 1. Well, you can consult back to your table of special trig values, and you see that this is going to come out to be theta equals pi over 4. And that's going to be our answer here. Take a moment to think about this, and now I want to go on to the next example, but make sure that you kind of re-watch this if it didn't make sense the first time, and you can always send me questions if you have any questions about this example. But I'm going to move on to thinking of another case here. So what about if I wanted to do sine inverse of minus square root 3 over 2? Well, in this case, I want an angle theta with sine theta equals negative square root 3 over 2. Once again, I need theta to be in the interval from minus pi over 2 to positive pi over 2. Sine is negative down in quadrant 4, so I need to pick an angle that's in quadrant 4. And the reference angle that we need here is going to be pi over 3. So my actual angle is going to be the angle down in quadrant 4 with a reference angle of pi over 3. If you think about what does that look like on the unit circle, that's going to be down here at negative pi over 3, because that's going to be the same size angle as this reference angle. So that means I get theta equals minus pi over 3. Now, what if we wanted to do a problem like the following? What if I had something like compute sine of sine inverse of 1/3? Well, if you do a trig function of its inverse, this is always just going to come out to be that number. As long as that number is inside of the domain for the inverse trig function that you're working with. Because notice that there is something special here about the domain and the range of sine inverse that follows from this definition, but that I haven't really said specifically. Now, I want you guys to take a moment here and see if you can figure out what would the domain and range of this inverse sine that we've defined be. Think about the definition of it, think about the range of the sine function itself, and ask yourself what this is going to come out to be. Okay, so the domain is going to be -1 to +1. Why? Because that is the range of the sine function. So this inverse sine, this doesn't make any sense if we plug in something that's not in the interval from -1 to 1. It only makes sense if I have something in here. Otherwise, there are no angles that would give me back some number that is outside of -1 to 1 here. So it wouldn't work with this definition. The range, well, the range, we basically picked it to be minus pi over 2 to pi over 2. So this example that we just did, this works fine. But if we wanted to do, let's say, sine of inverse sine of -3, this does not exist, or you can think of it as it is undefined. This is not defined because you can't plug -3 into the inverse sine function. It's not in the domain. So you got to be careful here. You can't just look and say, oh, it's function of inverse function, they cancel and they leave me with what's inside. You have to be careful because you have to be able to feed that -3 through the inverse sine and then back through sine. And you can't do that in this case, so they don't just cancel. They give you something that's undefined. Here's the other sort of tricky thing that you have to worry about when you're dealing with inverse sines and other inverse trig functions in general, okay? And this is when you do the inverse trig function of the function evaluated at some angle. Let's suppose that I want to do inverse sine of 5 pi over 4. Now, your first thought might be, oh, because we're doing an inverse function and a function, they should just cancel and give me 5 pi over 4, which is what we were plugging in the first place. This is unfortunately wrong. Now, pause this for a moment and see if you can see from this definition why that is wrong and what you need to do to fix it. Okay, so were you able to think of anything? Hopefully you guys were able to see. The problem is that 5 pi over 4 is not inside of this interval. It is not inside, whoops, I did not finish the brackets on my range. It is not inside of the range of sine inverse. So we want theta in minus pi over 2 to positive pi over 2 with sine theta equals sine 5 pi over 4. Now, one kind of easy way to see this, well, I don't know if I should say that it's easy, but the way that I like to think about this is if I sketched a unit circle, 5 pi over 4 would come out to have a terminal point here. So I can just reflect that over to here. Now, this angle is going to be a size of pi over 4. That's my reference angle. So this reference angle is also pi over 4 in size, and this angle comes out to be minus pi over 4. So we get theta equals minus pi over 4. And you can double check this. You can say, okay, sine of negative pi over 4, that would be the y coordinate of this point. Yes, that would be the same as the y coordinate of this piece. And this angle that we've picked, minus pi over 4, is in this interval from minus pi over 2 to positive pi over 2. So you really have to be careful here. And this is why writing sine inverse can be a little confusing. This is why some people prefer to write arcsine or asine instead, because it's not a true inverse of the sine function itself. It's an inverse to a special restriction of the sine function. So you got to be a little bit careful when you're thinking about that. And if you see arcsine or asine, that can remind you, oh yeah, this is not a true inverse. It's like an inverse in a lot of ways, but it's not really an inverse for the entire sine function, just for this restricted case. Okay, so let's take a look at the inverse cosine now. The inverse cosine is not too bad to do. I mean, it's kind of the same idea. We want to come up with a restricted domain. Now, if I were to sketch for you what the cosine graph looks like, it starts here at the top, and it comes down, and it goes down to negative 1 by pi. And it keeps on going. But the main point is that we hit the entire range over this interval from 0 to pi. And over 0 to pi, the cosine never repeats itself because it's always decreasing. So we define theta is equal to cosine inverse of x. Once again, you could write this as a cos or arc cos if you prefer. And some people do like doing that because just like with the sine function, we have this issue where we're going to have to worry about, oh, this is actually just an inverse on one restricted domain. This means that cosine of theta is equal to x, and theta is in the interval from 0 up to pi. So instead of going from minus pi over 2 to positive pi over 2, we go from 0 up to pi. Again, there's other choices you could make, but this is the one that everybody uses by convention. Now, just like with sine, there are some fairly straightforward kinds of questions we could ask. Like, for example, what is cosine inverse of 1/2? Well, this is an angle whose cosine is 1/2, and it has to be in this interval from 0 to pi. You think about that for a minute, and you realize, oh yeah, this is going to be equal to an angle of pi over 3. You could ask yourself, what is cosine inverse of negative 1/2? Well, this is going to come out to be 4 pi over 3. Again, you can find this just by looking at your table of values on the unit circle. And we can do the kinds of computations that we did before involving the sine function. So I will leave it to you guys to practice that sort of thing on your homework problems, and it goes very similarly to what we did with inverse sine. But what happens if we start combining them? So what if we have sines and inverse cosines and all this kind of thing? So for example, what if I wanted to ask you, what is the sine of the inverse cosine of 2/3? Your first thought might be, okay, let's see if we can compute what is cosine inverse of 2/3, right? Because if we could figure that out, then we could just plug that into the sine function and we'd be all set. Well, it's not, unfortunately, quite that simple in this case. The reason it's not quite that simple is because I don't know what this angle actually is. So we have a problem. We don't know the exact value of theta equals cosine inverse of 2/3. Well, that's a bit of an issue. And you might think that that means that this is simply an impossible problem to do. But it isn't. There's actually a way that we can handle this. The way that we can handle this comes back to the triangle idea of the trig functions. In other words, remember that when we talked about defining the trig functions, we said, okay, you define them in terms of the unit circle. But you can also think about them as giving you these ratios of right triangles, and that is kind of an alternate definition of them. So what we can do is we can say, we know that whatever this theta is, we can think of that angle theta as being in a right triangle. So I'm going to draw a right triangle with an angle theta here. And we know that the cosine of theta is equal to 2/3. But we also know something else about cosine theta. What do we know about cosine theta? Well, what is the ratio in terms of the sides of a triangle that you get from the cosine? Anybody remember? Hopefully you guys remember this. This is actually adjacent over hypotenuse. Because this is the adjacent side over the hypotenuse, I'm going to make a triangle with an angle theta whose adjacent side divided by its hypotenuse is 2/3. Well, if I make the adjacent side a length 2 and the hypotenuse a length 3, that is a triangle with the required adjacent over hypotenuse ratio. There's other choices I could make as well, right? I could have made this side, let's say, 20 and the hypotenuse 30. That'd be fine too, but why make things harder on ourselves than they need to be? The other thing that I know is that the sine of theta is the opposite side divided by the hypotenuse. In other words, this side here is going to be 3 times the sine of theta. It's the length of the hypotenuse, which I made as 3, times the sine of theta. But I also know that this has to obey the Pythagorean theorem. Now, at this point, I have kind of not a lot of space left down here, so I'm going to erase this up here and start working things from the top again. Hopefully you guys have this written down. So here's what we know. We know that 2 squared plus 3 sine theta squared is equal to 3 squared. And I'm going to erase this as well, and hopefully you guys can just keep that in your notes here. So this means that 4 plus 9 sine squared theta equals 9. This means that 9 sine squared theta is equal to 5. Sine squared theta is going to be equal to 5/9, and that means that the sine of theta is plus or minus the square root of 5 divided by 3. Now the problem that we have here is we need to figure out, should we take the plus or the minus? And the answer is, ask yourself about quadrants. We know that cosine inverse of a positive number has to sit in quadrant 1. So we know that theta is in quadrant 1. That means I want to take the positive root here. So my answer is going to be positive square root 5 divided by 3. And that is the value of sine of this cosine inverse of 2/3. Little bit of a complicated process when you first see it. Once you get comfortable messing around with triangles and stuff, it's not too terrible. But you do have to remember, every one of these problems is going to require you to build a triangle. The other thing you have to remember is that sometimes you actually kind of have to think of building the triangle with a reference angle instead of just building it with the angle itself. So let's take a look at that kind of thing. Suppose that I want to find the cosine of sine inverse of -4/5. So this is going to be an angle theta. We're looking for cosine theta, where sine theta is -4/5. Also, theta needs to sit in the interval from -π/2 to +π/2. Now, whoops, sorry, there's no equal sign there. I should say sine theta equals -4/5, not sine of theta times -4/5. What I'm going to do is say that this means that the reference angle, theta reference, has sine of theta reference equals 4/5. Now, why do I want to think about a reference angle here? The reason I want to think about a reference angle is because I want to build a triangle, so I want to think about some angle that is between 0 and π/2. And the original angle is probably not going to be that. In fact, it's definitely not going to be that because it comes out to have a negative sign. So what I can do now is I can build a triangle. Now, I want to build a right triangle with an angle theta r, and I want the opposite divided by the hypotenuse to be 4/5. Well, if I make the opposite side 4 and the hypotenuse 5, that is certainly going to manage it, right? Well, that means that this side is going to be 5 cosine theta r. Okay, so what does this mean? Well, this means that using the Pythagorean theorem, we get 5 cosine theta r squared plus 4 squared equals 5 squared. This is going to mean that 25 cosine squared theta r plus 16 equals 25. This means 25 cosine squared theta r, I'm sorry, I'm completely blocking what I'm writing, is equal to 9 cosine squared theta r equals 9/25. This means that the cosine of my reference angle is actually plus or minus 3/5. But now, because this is a reference angle, I know that we want to take the positive for the reference angle. However, I'm actually interested in the original theta. And the problem is that since the theta comes out to be negative, that means that what we can say is that theta is in quadrant 4. So cosine of theta is plus or minus 3/5. But theta is in quadrant 4. So let me ask you this. Think for a moment, is cosine positive or is it negative in quadrant 4? Well, it's positive, right? Because on the unit circle in quadrant 4, the x-coordinate is always going to be positive. So that means that the cosine of theta is going to be the positive option. The thing that we know is that the cosine of theta is always plus or minus the cosine of the reference angle, and then we use the quadrant to say should it be positive or should it be negative. Okay, so hopefully that example made sense to you guys. Now, I, again, want to emphasize, you need to practice these kinds of things because there's not just a formula that you use. I can't just hand you a formula and say, plug the numbers into this and it'll give you the answer. You have to get used to building these triangles, but It's one of those things where once you've gotten the hang of it, like once you've done 10 of these, you sort of start to just automatically see what you're doing, and you can do them pretty easily once you get used to them. You know, maybe they're not the easiest kinds of problems to do, but there's nothing that is too different about any of these problems. You do have to just remember, every time you build the triangle, you need to build the triangle with the right properties for the given problem. Okay, so next week we're going to start talking about what about the other inverse trig functions. What about things like inverse secant, inverse cosecant, inverse tangent, inverse cotangent? It turns out that we can do a very similar kind of thing to what we did here with those things as well. And similarly to what we did today with finding these kinds of things, when you start talking about the other inverse trig functions, again, you often can solve your problems by just building a new triangle. So that is what we're going to start talking about in the next lecture. In the meantime, good luck with the upcoming test. Make sure to do the practice test before you do the real test, because once you start the real test, you can't just stop it. You have to kind of do it all in one sitting. And do let me know if you have any questions before then from the practice test or anything else, so that hopefully we can clear up any questions that you might have before you start trying to take the actual test. Anyway, I will post another video for you guys soon.